Hello everyone, welcome to Chapter 4, Applications of Derivatives. Here we look at Newton's method. This is a comparatively shorter section. And why Newton's method? Well, it's a technique that we use to approximate the solution of a function. So what does that mean? Let's say your function was given to be f of x, and we need to find the solution. What that means is that we will automatically set f of x to 0 and then solve for x, because solution means to find x. We'll find x where f of x, the function, becomes 0. If you're looking at this graphically, let's say, then we are looking at maybe a graph that looks like this. Then we're interested in these points, because that's where this function, because your function is this curve, your f of x becomes 0, right? Because that's where the function becomes 0 at those points. So we're interested in knowing what these points are. So graphically, we know that these points would be your x-intercepts. And there are several other names for this. Now, we just saw that we use the word solution for this. We also call them as roots. And there's another name also called zeros. They mean the same thing. They are just different names to indicate different representation, right? For instance, x-intercepts is a representation of where the graph crosses the x-axis. And therefore, it is a visual thing, and so we use this language x-intercepts when it's a graphical representation. On the other hand, we use the language solution or zeros when we want to do them algebraically. Okay. So again, in algebra, we use the language initially as solutions, but when we got to intermediate algebra, more advanced level, we call them roots or zeros, because we were able to set the function to 0 to solve for x. So then, why Newton's method? We can easily solve this. We've been solving this in algebra, so what's the big deal here? Well, this is what happens. Now, if your function, say f of x, was given to be a polynomial of degree 1, right? This is a polynomial of degree 1. It's basically a linear function. If we need to find the solution for this, you will set this to 0, and actually you can solve for x, right? Subtract b on both sides and divide by a. No matter what b or a will be, you can go ahead and find the solution. Now, if I gave you f of x equals ax squared plus bx plus c, this is a quadratic equation, and we know how to solve quadratic equations. So we solve for x using, there are so many ways we can solve, meaning we can factorize it by using the GCF, the AC method, BC method, basically, factoring by grouping. We could also do the completion of squares, square root property. All these are different shortcuts to help us get the factorization. But we've seen that, quadratic formula works perfectly for all these methods. If you were to combine all these methods in one stop shop, that will be the quadratic formula. So we have a way to solve if it is a polynomial of degree 2. But imagine for polynomials of degree 3 or more, finding the root for f becomes super complicated just because of the various methods that we could employ and still not find the answer. For instance, we have the rational zeros method, and that is a lengthy process if you end up having numbers in your equation that are with more factors. Then you have plenty of trial and error that you have to do in order to find the solution. So now we want to do all these without looking at the graph, right? To do them manually, I mean. If you're using a software, we really have no problem. But we're talking about getting these manually. So imagine I gave you an equation like this. X power 5 plus 8x power 4 plus 4x cubed minus 2x minus 7. To do this manually, meaning to set this equal to 0, you have to find x, and it's not just one x. Because of the polynomial of degree 5, you'll expect 5 x's, 5 solutions for x. So you can already see how it's going to be super difficult to even get the first answer. Because when it's a polynomial of degree 3, there's little help there, because if you found one solution, you can use that to find the other two solutions using quadratic. But here it becomes all the more complicated to even find the first solution. And then even then it doesn't really help you to find the remaining 4. What about non-polynomial equations, like say tan x minus x? As simple as it looks, when you set it equal to 0, it's difficult, it's complicated to find x for this, an x that works, that solves the answer here. So for all these cases, we'd like to use the Newton's method, and the whole idea here is to approximate the solution. So Newton's method helps us to approximate the solution using the tangent lines, because we are talking about applications of derivatives, so there is that tangent line derivative coming there. So we will use tangent lines, and therefore we will be using linearization, what we saw before, like differentials and linearization. So we're going to use these two techniques to help us find or to help us approximate the solution for a given function. So Newton's method basically involves the first derivative tangent line. I have summarized the pertinent points here, where Newton's method is basically a technique to approximate the solution to an equation f of x equals 0, as I mentioned before. We will be using tangent lines. The deal here is that where your function is 0, that is where the root is, isn't it? So if we can find where the function is 0 using the tangent lines, which I will illustrate shortly, then we can approximate the solution. And to do this, we produce a sequence of approximations using linearization. Again, linearization comes from the idea of derivatives and using the equation of a tangent line, which is basically y minus y1 equals m times x minus x1. So it is all old stuff that we are renewing each time to help us determine a solution to a complicated equation. So to illustrate that, I have this graph for us. So look at this curve here. This curve, this one, is your f of x. Okay, that's given here. So that's your f of x, that's your curve. And visually speaking, we want to find this answer here, right? That is where your function, your f of x, is 0, because that's your corresponding y value, right? F of x is 0 at that point. We need to find this x value. And in order to do that, we are going to begin by finding the tangent line, okay, at a particular point. So for that, let's say, you know the solution happens here. We just don't know what that x is. So choose a point anywhere closer to it in that neighborhood, because that's something we can see visibly. So choose that point. For instance, let's say we started off with x naught. X naught is a point that's close to this x. And so at x naught, if you draw a tangent line, you can get that tangent line, if you stretched it, it can hit x1. Okay. So again, this is true only if that tangent line was not a horizontal tangent. Because say you got a horizontal tangent, then you can't really stretch it to meet the x-axis. There will not be an x-intercept, isn't it? So you can find a value in the neighborhood of your expected solution. Another way is, we've seen before, is where you take the first derivative and set it to 0, isn't it? Because that is where you find if it is not equal to 0, right? So in other words, if you can find the first derivative where it is not equal to 0 at a particular point, then that tangent line will give us, if you extended that tangent line, it will cross the x-axis, because every slanted line will cross the x-axis. Will have, because you're stretching it indefinitely, at some point it will cross the x-axis and the y-axis, isn't it? This may not be true for a horizontal line that is not passing through the x-axis, because if you have a horizontal line that coincides with the x-axis, yes, okay. But if it doesn't coincide with the x-axis, a horizontal line will will not cross the x-axis ever. It only has a y-intercept. It will not have an x-intercept. And a vertical line, again, we are not talking about vertical tangent, right? That will make it undefined. But I'm talking about any slanted line, a tangent line that is slanted, like in this case, will have an x-intercept. That's what we're trying to capitalize on. So we extend this this tangent line, and that hits the x-axis at x1. So find the corresponding value x1, f of x1, and at that point draw another tangent line and stretch that tangent line. So this is the sequence of approximation, linearization that we're doing. So draw that tangent line, that hits at x2, and then go for the corresponding point at x2 and draw a tangent line there and stretch that tangent line, and keep doing the sequence of producing these tangent lines that hits the x-axis at a particular point. And what happens is eventually you'll come across the x value where your f of x will be 0. Okay, so that is the whole point. And for that we use Newton's method of approximation, which will help us to speed up this process. It is iterative, meaning you'll have to keep repeating this process, but then there is a format by which we repeat this iteration. We will look at that first as general steps, and then we will look at a problem. The Newton's method contains 2 steps. First is to guess a first approximation to a solution. So you're looking at the neighborhood of the answer, because you kind of see where it's going to cross the x-axis, where the graph will cross the x-axis. And of course a sketch of a graph would help. And then look at the closest point that you can begin to apply the approximation. So we're saying guess the first one for to get started. Step 2 says use this first approximation to get the second approximation, use the second to get the third, and so on. And to help us do that, we have this formula. Technically, this formula again comes from your equation of a tangent line. So we're going to use that information to help us generate these points. And so once you keep generating these points, we will come across a value for x where the corresponding f of x will be a 0, or because we're approximating, it may not be exactly 0, it may be very, very, very close to 0. So we're going to look at an example. I'm going to use a very simple one just to illustrate how we can compare the answers. So remember, this is very helpful in more complicated equations, but let's start off with a simple one. The question says, find the positive root of the equation f of x equals x squared minus 2 equals 0. They're already setting it to 0 for us. We need to find the positive root. Now, because of the simplicity of this equation, we know that we don't really have to use Newton's method because if f of x equals 0, it implies this x squared minus 2 equals 0. You're trying to solve for x, isn't it? So add 2 on both sides. X will be plus or minus root 2. But the answer said, the question said, find the positive root. So this implies x is positive root 2. You kind of got the answer here. And we're going to keep this aside, but use Newton's method to arrive at this answer, or at least to get the approximation to this answer. This is the exact answer, but we're going to find an approximation to this, which is acceptable enough. So let's begin by first taking the Newton's method formula, which said xn plus 1 equals xn minus f of xn over f prime of xn. Sometimes, you could simplify this equation even further depending on your equation, because this is all in generalized form. You can make it specific to your equation based on this formula. So I'd like to take our f of x here and then use that to find the derivative. That will be 2x, isn't it? This is for any x. If we wanted a particular x, which is xn, then this would become, your x's will be replaced by xn, isn't it? And f prime of xn would be 2 times xn. So I'm going to use this to substitute in xn plus 1. So xn plus 1 will be xn minus, f of xn is x squared minus 2, sorry, xn squared minus 2 over 2 xn. So you can think of this as xn minus xn squared over 2 xn. I'm separating by distributing. So plus 2 over 2 xn. Simplify this, and one of the xn's will go away and the 2's will go away. So we are left with xn minus xn over 2 plus 1 over xn. Combine these two, right? So that's 1 minus half, so that's basically half. So xn over 2 plus 1 over xn. It doesn't work always like this. Sometimes you'll just have to substitute values. I will show you another problem like that. But I wanted to show you that in places where you can simplify it based on your given equation, we want to always do that because it makes life so much easier for computation purposes. So we now, because we're going to build a sequence, it is important to build a table because it's easier when it's tabulated for the approximations. So we definitely need two columns. I should say 3 columns because one to generate different x's. So I'll just say x, f of x, and xn plus 1. This is xn. So we have 3 columns, and for this equation, okay, for this one, x squared minus 2, we need to start with some value, right? So if you were interested in sketching the graph of this, this is a parabola, isn't it? Where shall I sketch it? Okay, I'm just going to squeeze that in here. This would be y equals x squared. Though this is x squared minus 2, that means this went down 2 steps, right, using transformation. So this is minus 2. And so from here, you are trying to see the positive root, because you have your x intercept happening here and here, but then you're interested in this only because we want the positive root. So for that, you want to look at the coordinate there. So for that, again, you have to graph it in such a way that you get those coordinates, at least in the neighborhood. Okay. So when x is 1, plug in here, okay, to get your f of x. When x is 1, 1 squared minus 2. 1 squared minus 2 will be minus 1. So the y coordinate for that will be minus 1. And when x is 2, 2 squared minus 2, 4 minus 2 will be 2. So you're going to keep that as your reference. And then we know that 1 is this side of the graph which crosses the x-axis. And so we want to start from 1 and see if we can do the approximation to approach this value. So I am going to start with x naught as 1, because that was the first step, right? If you go back here, it said guess a first approximation to a solution, and a graph may help. So we sketched the graph and we found that 1 would help us to get to the answer here, because 2 would be, we just saw, right? 2 would be 2 squared, which is 4 minus 2, which will be 2. So that's going to be a value, the f value for that will be on this side. So this graph will be between 1 and 2. Okay, when x equals 1, what is f of x? So you're technically going to substitute for 1 squared minus 2, which was negative 1. But we need to find x1 using this approximation. But we know that because of this simplification up here, that will be x naught over 2 plus 1 over x naught. X naught is 1, so half plus 1 over 1. So half plus 1, which is 1.5. We want to keep them as decimals because it's just a computation to the approximate value, so it doesn't have to be in fractions. It's a lot more easier when you keep them as in decimals for computation. So your x1 now is 1.5. Use this to compute this. That gives us 0.25. Okay, the reason why I have the f of x column is we want this number to be 0, or at least very close to 0. So you want to see that number getting close to 0. If not, you're moving away from the root. Okay, that's an indication that your original guesswork of 1 was off. But here we did the sketch of the graph, so we are confident that we won't be off. Okay. Then we have x2, which is x1 over 2 plus 1 over x1. So if you computed that, that will be 1.5 over 2 plus 1 over 1.5. Of course, use your calculator to get this. And try to get as many decimal places as possible to get a more accurate answer. So x2 is 1.416667. Plug that in for your f of x. The corresponding value is 0.00695. I'm not showing the computation, I'm just giving you the final answer here. And then x3, using this x2, x3 comes out to be 1.41422. When x3 is 1.41422, the corresponding f of x comes out as 0.000018. In fact, you can go with x4 as well and see what happens, if it exceeds or does it go beyond 0. But what we see here is very, very significant because this is very close to 0. That means this must be the solution for the given function. When I say solution, of course, I mean approximate. So I'll just say approximate. We're already rounding things, so it is definitely approximate. So what we're saying then is that this x equals 1.41422 is the approximate positive root for f of x equals x squared minus 2. But we already found the solution by just solving for x. We got x equals root 2, okay, from solving for x without using the Newton's method. Now take your calculator and compute square root of 2. And to your surprise, you'll see that that is actually giving us this very answer. In fact, it gives us 1.414213562. So if you were to kind of look at the answer we have, the approximate answer we have, you can see how nearly close it is for up to 4 or 5 decimal places. And so that is how at least how mathematicians used Newton's method in doing their calculations way, way, way before we had the calculators, especially the scientific and the graphing calculators. So it's really a powerful method to help us find the solution for more complicated equations. So to illustrate that, let's do another example. Use Newton's method to approximate a root of f of x equals x cubed minus 3x plus 1 in the interval 1 to 2. Let x naught equals 2, or let x naught be 2, and find x1 through x5. Very specific instructions. Newton's method is what we should use, so we are clear about what to do there. And it said to approximate a root. You have to be very, very clear about how the language is indicating us to find one of the roots. Why one of the roots? Because we know there will be 3 roots because of the degree 3. There will be 3 roots, and we're asked to find one of the roots, and that too in this interval 1 to 2. So we want to, and we're also told what a starting point should be. They're saying let x naught be equal to 2, and then want us to find this. So very, very interesting here. In fact, you can do the sketch for this graph and do that, or look at your graphing calculator. And in fact, that comes out to be, I'm just doing a rough sketch here. So it looks as if we have the graph going like this, something like this. It has to be a smooth curve. Very clearly, we have a root here. We expected 3 roots, right? So we have a root here, here, and here. And we want to find the root between 1 and 2. So again, I'll give you a little hint here. If you looked at the graph, there's 1 here, and then there will be 2 here. Okay? So we have roots in other places, but we need to find this one. This one is what we need to find. It's between 1 and 2. We want to approximate it as close as possible to the actual answer. So let's go ahead and use this. Now, if they gave us x naught equals 2, we could have used 2 to be a starting point just because of the interval that they gave us. So if they didn't give us that interval, we could have we would have used the graph to help us to get the closest starting point, a guess point for us to begin our approximation. We have to write what we just observed. F has 1 root in the interval 1 to 2. Okay. X naught is equal to 2. So you can build a table and get your corresponding values. But here they made it very specific. They said find x1, x2, x3, x4, and x5. So in this case, I really don't want to build a table just because we are not asked to find the solution technically, in the sense we are asked to find the root, yes, but we are asked to find these specific values. So the f value, we will use them, of course, indirectly to compute our values. So let's go ahead and get our f of x here. So that f prime of x will be 3x squared minus 3. So since x naught is given to us, let me write the formula again. Xn plus 1 is xn minus f of xn over f of f prime of xn. X naught is already given, so we'll start with x1. x1 will be x naught minus f of x naught over f prime of x naught. You can do this in a table too, but I just feel I need more room. Oh, I'll just start plugging in values here. So x naught is 2 minus f of 2 over f prime of 2. You can pause the video now and then, calculate these things. Plug in 2 for x in your f of x and f prime of x. And that will give us 2 minus 3 over 9, which is approximately 1.666. Try to, the recommendation is that you go for it up to 10 digits. But again, if your calculator can display that many digits, when you're using a graphing calculator, it should. But anyways, try to get as many as possible, is the point. Then x1 is that. So x2 will be x1 minus f of x1 over f prime of x1. You can immediately see how it becomes challenging without a calculator. 2, 3, 4, 5, 6. Okay. That is approximately 1.54861111. Okay, so we found x1, x2, now it's x3. x3, gives us approximately 1.532390162. x4 will be x3 minus f of x3 over f prime of x3. It's getting really long, so I am not going to enter that here, but I again urge you to pause the video and compute it yourself and cross-check with the answer here, because we need to go up to x5. That's what they wanted, so we have that. And this comes out to be approximately 1.532088989. x5 will be x4 minus f of x4 over f prime of x4. That gives us 1.532088886. Okay. What is there something you notice? As we were kind of done with the problem, we found all the values, but they asked us to find the root, okay, using these values. So then you have to go back and see what's happening, because we didn't really figure out what f of this x5 is. You should, just to cross-check. You probably did that when you did this computation, right? x5. When you did x5, you did find f of x4. So what is f of x5 itself? If you actually took the time to compute this, in fact, f of x5, right? Because remember, we were trying to get the x value where the f becomes 0. So when you compute this, your calculator will give something like this: negative 9.618, says E, or it just says negative 10 right next to it. What does this mean? This means it's negative 0.123456789. That's the 10th one. 618. That's what this means. You see how very close to 0 it is? So we are approaching the answer. In fact, if you go back to our graph here, remember we started at 1, right? So this is where we started. We did the tangent, and then that hit somewhere, and then so we're getting closer and closer and closer to 0. And so we're approaching it from under. That's why you have that negative. And then as we get closer and closer to it, you are actually hitting 0. So in fact, if you wanted to go further and find x5, x6, that's going to be x5 minus f of x5 over f prime of x5. You'll be surprised to find that gives us an approximation of 1.532088886, which matches with x5. So we are hovering so close to it right there. Okay, and that actually is the answer. So we know that our root is the same value as x5 and x6. Therefore, if you did any subsequent application of this Newton's method, it will most likely give the same value for xn. Right? So then we say f of x has 1 root 1.532088886 between 1 and 2. That is our answer here. So coming back here quickly just to check our graph on this. Oh, you know what, actually, this would have been, that's a 2. This would have been pretty much here, somewhere here, right? Because we got 1.5, what was it? 1.5486. So that means it was very close to the 1.5 mark. It was very close to this. And then it moved closer and closer to 0. Alright, so that is it, class, for this section. As I mentioned, this is a short one. And Newton's method is kind of covered here. I will see you in the next video in chapter 4.